Hi ladies, in this video we're looking at 8G independent events. So independent events kind of mean that the probability of one event does not affect the other. So if you think of the word independent, it means they're independent of each other. It doesn't necessarily mean they're mutually exclusive. Okay, so they're two different things, but independent just means the probability of one event does not influence the probability of another event. So I'm going to just skip back to the textbook because I feel like the textbook actually explains it quite well. And I wonder if I can make that just a little bit bigger. Okay, so in a Venn diagram, which you can see there on the right-hand side, we've got some numbers. And you can use a Venn diagram to help you understand whether events are independent. So for this one here, we're going to look at event A and B. Now, the probability of A, as we look in the circle for A, we've got 5 and a 2, so 7 for A, out of how many? There's 10 in total. So 5 plus 2 plus 3 gives us 10. Now, the probability of A given B, okay, so this is conditional probability of A given B. So we have the intersection 2 given B is 5, so 2 over 5. Now, because they're different, these events are not independent. Okay, so they're not independent of each other because the probability of getting A given B is changed by B. If it was the same, A would be independent. But because the probability of A changes when you take into consideration B, okay, so effectively B is changing the probability, they're independent of each other. Now, if we look at multi-step events or multiple events in this tree diagram, okay, so this time we're selecting, and this will probably make a little bit more sense. So we've got marbles in a bag, 2 are aqua and 3 are blue. So obviously if I select an aqua bead and then I put it back, so I'm replacing it, taking it that first time is not going to affect my probability for the next pick. It's the same as if you were to toss a coin. Okay, every time I toss a coin, it's equally likely to get a head or a tail. Okay, that doesn't change. Just because I got a tail one time doesn't mean it's going to affect whether I get a head or tail next time. It's still going to be 50-50. So it's the same here with replacement. Okay, so the probability of getting an aqua bead stays 2 over 5. Now, what this symbol means here is A given A. So we've got the second one is aqua, given that we've already chosen an aqua. So this is usually what it is anyway on a tree diagram. We just usually would write A, but it is effectively A given A. And we do the probability of A and A. So they're our outcomes. It's just another way of writing our outcomes. Usually we would write AA, but it's the same as A and A. And for the purposes of looking at independent events, it just helps to use this notation. Okay, so we've got now, if we chose a blue marble, the probability is 3 over 5. So the probability of getting a blue marble on the second time, given that the first one was aqua. Okay, so that's how you would read that tree diagram. Now, what we know when we think of this bag of marbles, my first selection of aqua or blue doesn't affect whether I select an aqua or blue the next time, because I'm putting that marble back in the bag. Now, if it was without replacement, if I take an aqua bead, okay, if I've taken an aqua bead and I don't put it back, it reduces, first of all, how many aqua beads I have in the bag, but it also reduces how many beads I have in the bag. So that's not independent. Okay, so selecting the second marble is not in, the probability of that is not independent of what I did the first time because it's changed. I've kept that aqua marble out of the bag and it's changed the probability. Now, all these symbols or notation is used to show you how we can use these formulas for independent events. So for independent events, the probability of A given B is equal to A. So if we look back up here, we know with replacement, they're independent. Probability of A given B, which we can see, I wonder if I can highlight here because I can't draw in a PDF, unfortunately. A given B is the same as, which is 2 over 5, which I can't really highlight too well, is the same as this, the probability of A. Okay, so they're the same, so it shows that they're independent. Now, that goes on to imply that the probability of A and B over B, so that's conditional probability formula, becomes the probability of A. So independent events, A given B is equal to A. So it's the same formula, but we've got, instead of A given B, we've got the probability of A. So when they're independent, the probability of A is the same as the probability of A given B, which means that this is the same. Okay, so that's just explaining how the independent events work. And we can rearrange this formula here, which I've just highlighted, to become this. Okay, so when two events are independent, we know that the probability of A and B is a probability of A times the probability of B. Okay, lots of stuff there to think about. Okay, so you need to probably apply this to some questions because it is quite confusing. I find independent events probably the most confusing of the topics in probability, and sometimes it's not as easy to explain. But these 2 points here, just think you've got a bag of marbles. I take one out and I don't put it back in. So if I take another marble, the probability is going to be different. So they're not independent. But if I put that marble back, they're independent. Okay, so with replacement, what we've got here, I might just highlight it, with replacement, independent. Without replacement, not independent. When you think of flipping a coin, okay, the probability doesn't change. Okay, each time I flip that coin, it's going to be the same, 50-50. Okay, I roll a 6-sided dice. The probability of getting a 2 will always be 1 over 6. Okay, so the probability doesn't change. So the event is independent. But when you've got without replacement, it's not independent. And I probably should have underlined this not as well. Okay, let's have a look at question 1. A selection of 8 offers for computer printers includes 3 with a printer cartridge and 4 with a free box of paper, whereas 2 have both a free printer cartridge and a free box of paper. So we need to, A is choosing a printer with a free printer cartridge, B is choosing a printer with a free box of paper. So let's draw it as a Venn diagram. That was a terrible circle. Now, when I was marking your work, a lot of girls didn't put their rectangle around their circles. You need to put that in, girls. Okay, so we've got 8 offers. So 2 have both a free printer cartridge and a free box of paper. So I'll put 2 in here. That's event A, event B. A is choosing a printer with a free printer cartridge. So 3 you get a free printer cartridge with. So we've already included 2 of those, so we put a 1 here. And 4 with a free box of paper. So we've already included 2, so we'll put a 2 here. So I've already got 5 offers. So that means 3 must be something else. Okay, so question B, find the probability of A. So the probability of A is, we've got 3 over 8. Okay, so 3 and A over 8 offers in total. The probability of A given B. So this is the conditional probability. Hopefully you can remember the conditional probability formula. So A given B. So how many in common? 2 over 4, which is a half. State whether the events whether or not the events are independent. So remember, for them to be independent, the probability of A given B must be equal to A. Are these equal? Does 3 over 8 equal a half? No, they don't, so it's not independent. Okay, so that's all you need to do to state whether they're independent. Okay, so question 3, from events A and B in the given Venn diagrams, find the probability of A and the probability of A and B, sorry, A given B, and then decide whether or not A and B are independent. So let's do each one. So the probability of A is 3 over 4. The probability of A given B is 1 over 2. Okay, so we're intersection over B. Are they equal? No. Okay, so 3/4 is not the same as a half, so not independent. Question B, probability of A is 7 over, what do we got, 28. Probability of A given B is 2 over 6. Sorry, not 6, 8. Okay, so we need to just simplify them. So 7 over 28 is a quarter, and 2 over 8 is also a quarter. Now they're the same, so that means they're independent. Probability of A is 5 over, what do we got, 10, 15. If you want to simplify that now, you can, which is a third. The probability of A given B, so is 3 over 9, which is a third, so they're independent. And here we've got the probability of A, which is 2 over 7. The probability of A given B is 0, because there's no intersection, so that's not independent. All right, for question 4, sorry, I paused and then I did some scrolling, so I probably jumped straight to this. For the events A and B with details provided in the two-way tables, find probability of A and the probability of A given B and decide whether or not they're independent. Okay, so let's find the probability of A first. Okay, so we're out of a total of 8, and the probability of A is 4, so 4 over 8. You can simplify that, but I just don't have any room on my page. A given B, remember, is the intersection of A and B, so that's 1 over the probability of B, which is 2. So 4/8 is equal to a half, so they're independent. For B, we've got the probability of A is, where are we? 3 over 10. Probability of A given B, so we want the intersection, which is 1, over the probability of B, which is 4, so they're not independent. So guys, if you're wondering how I'm doing A given B, you need to go back to the conditional probability formula. So the conditional probability formula is just the intersection of A and B over the probability of B. So I'm just doing that, but I'm not writing the formula down. Okay, the probability of A here, we have that's out of 36 and 15. I can simplify that if I want to, but we'll see how we go without doing it. A given B, so 3, B is 20. Okay, so I can see that they're not the same simply because, they're not the same. I don't need to simplify 15 over 36 to see that, so not independent. Here we need to complete the two-way table first. So remember, your columns all have to add up and your rows all have to add up. So we just need to complete this. There we go. All right, probability of A is 5 over 45, which is 1/9 if you wanted to do that. And the probability of A given B, so is 1 over 9, so they are the same. So they're independent. Okay, so A and D are independent. All right, some more questions. So a fair coin is tossed 5 times. Find the probability of obtaining 5 heads, at least 1 tail, at least 1 head. All right, for question 6, sorry, I just have to pause there and have a drink. I've been talking for so long. So this is here because they're independent, okay? So as I said before, tossing a coin or flipping a coin is always going to be 50-50, okay? So 5 heads, we want the probability of getting 1, 2, 3, 4, 5 heads. Now you could draw that as a tree diagram if you want to, but that's one huge tree diagram. But when you think about the branch that you're doing, it's kind of going like this, yeah? And along the branches, we've got a half, it's a half, 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 and just because I had one more to go, I'll put that in as well. So we're just multiplying these, okay, along our branch. And I know I showed it as a tree or a branch on a tree diagram, but they're independent, okay? So getting ahead the 5th time does not matter what you did the previous times. They're all independent of each other. So we've got a half multiplied by itself 5 times. So knowing your index laws, so that's 1 to the power of 5, which is 1. 2 to the power of 5 is 32, or you could just do that on your calculator if you wanted to. Okay, question B. At least 1 tail. So basically, we want the probability of getting greater than or equal to 1 tail. So we want 1 minus no tails, all heads, which we just did. So that's going to be 31 over 32. So it's highly probable that we're going to get at least 1 tail. And then the last one, at least 1 head, is going to be exactly the same. At least 1 head, because the probability of getting a tail is the same as getting a head. Okay, so 31 over 32 for both of them. All right, sorry guys, I keep pausing and then I forget what I've already spoken about. Question 7, a fair 6-sided die is rolled 3 times. Find the probability that the sum of the 3 dice is 18. So let's have a look at that down here. So this is a question here because rolling a dice is independent, okay? Every time we roll it, we're going to have a 1 in 6 chance of getting the number. So for A, we want the probability the sum is 18. Now, the only way that we can get the number 18 is to roll a 6, a 6, and a 6, okay? So we're adding them all together. There's no other way that we can get a sum of 18 other than getting 3 6s in a row. So the probability of getting 1 6 is 1 on 6, another 6 is 1 on 6, another 6 is 1 on 6. So if you think of it as a tree diagram, we're just reading these probabilities as we go along. Multiplying these together, multiply your numerators. So you got 1, 6 times 6 times 6, 216, or you can use your calculator if you can't do that. Okay, probability of getting a 3. So I'm just going to write this here. Now to get a 3, we must, so we've got rolling it 3 times, we have to get 3 1s in a row. Okay, so that's also going to be 1 in 216. Same thing, because the probabilities of getting 6s is the same as getting 3 1s in a row. All right, question C, which is 4. Okay, so the probability that the sum is 4. Okay, so when you think about your 3 dice, you can have a, let me just think, a 1, and a 2. You can have a 2, a 1, and a 1. And you can have a 1, a 2, and a 1. Now, because they're independent, the probabilities are going to be the same as they were here. So they're all still going to be 1 over 216. And think of them, if you could, as a very large tree diagram, which has 260 branches at the end, or different outcomes. But we just add these up. So we've got 3 out of 216 possibilities there. Okay, so 1, 1, 2 is the same as getting 1, 1, 1. Okay, so 3 numbers in a row, but there's 3 different combinations that we can have to make up the number 4. All right, and there was one more number, number 5. So the probability of getting a 5. So you can just list your probabilities. We can have a 1, a 2, and a 2. We can have the same as before. Well, 1, 2, 1. We can have a 2, 2, 1. We can have 1, a 1, and a 3. So I'm forgetting to put my commas in. We can have 1, 3, 1. And then we can have 3, 1, 1. 3, 1, 1. And the probability of all of these is still 1 over 216. Okay, so the probability for all of them is still 1 over 216. So I'm not going to write that for all of them. But how many outcomes do we have? We've got 1, 2, 3, 4, 5, 6. So the probability of getting a sum of 5 is 6 over 216, which can be simplified to 3 over 108. And 3 does go into 108. How many times was that? 26? I think, let me just quick, no, not 26, 36. 36, there we go. Should be writing my equal signs. All right, I hope that's the last question. Otherwise, it's a very long video. Cool. All right, girls, bye.